Okay, quick recap on the internal energy part 2. Now we are talking about application. So in the previous short capture, we talked about what is internal energy. So right now we look at how do you use it. Okay, especially when we are giving you a heating curve such as this. Okay, so the heating curve over here we separate it into different parts. So you see you have segment AB, segment BC, segment CD, segment DE, and segment EF, right? So these different segments represents different stages of what happens to a substance when given to you in solid state. Okay, what happens to the solid when it's being heated up? Okay, what do you observe as well as what is actually happening inside? All right, so let's first talk about A, B, C, D, and E, F. These are the ones where you notice there is a change in temperature. Okay, so there's an upward curve, right? So what you will see is actually there is a temperature increase, right? So the icon that I've drawn over there is just an eyeball, just to remind you that this is what you see physically, right? Temperature increase. Okay, there is no change in state. Okay, so in terms of what you can see when I draw the blue circle, is actually trying to represent the particle. So in the form of the particles, actually the kinetic energy, internal kinetic energy will increase, particles are actually vibrating more vigorously. Okay, whereas when we talk about BC, we notice that the temperature is constant, so in this case substance is melting. There's also another portion of the graph where the temperature is constant, and we notice it's actually DE, right? Okay, so for DE, it's not melting, but it's actually boiling. Okay, so what is actually happening to the particles? Alright, how do you explain why is it that the temperature is constant? Okay, so the bonds between the particles are broken or overcome. Alright, so the distance between particles are now increased, and therefore internal potential energy of the substance increases as well. Okay, so then now let's move on to what happens if I'm giving you the opposite, which is actually in the form of a cooling curve. Okay, so what if I draw a cooling curve like this? Okay, uh, so if I were to draw a cooling curve like this, we have the different segment A, B, C, D, E, F, where you notice the temperature decreases, the state remains the same. Right, so starting from gaseous state, right? Okay, the temperature decreases. Right, so particles slow down, less vigorous, internal kinetic energy actually decreases. So that's the way we explain about what the particles are doing, right? Okay, for B, C, and D, you notice that the temperature is constant. All right, the state remains unchanged. Change. So for BC, it's actually changing from gaseous state to liquid state, and for DE, it's actually changing from liquid state to solid state. All right, so this is a cooling curve. So the substance is actually cooling down, changing from gaseous state to liquid state, from liquid state to solid state. So this is what we see. What happens to the particles then? Okay, so I'm going to give you one whole chunk of text over here. A few ways to understand this. Okay, so you break it down. Right, the particles come closer together because it's colder. Right, energy has been released. They move less vigorously, so they come closer together. Internal potential energy decreases. All right, because the bonds are formed, energy are released. Okay, so when they form bonds, internal potential energy decreases. Particles are closer together. Right, so you can relate it to gravitational potential energy. The further the distance between the particles, the higher the internal potential energy. The closer between the particles, the smaller or lower internal potential energy of the particles. Alright, so take note that the internal kinetic energy at this point remains unchanged. Now we still have one more segment, right? FG, there's no change in temperature. That's what you observe. So actually what is happening? Okay, because it has the same temperature as the surroundings, therefore there's no net gain or loss of internal energy, and hence it remains constant. Okay, so Fg, although there is no change in temperature, because from B to C and from D to E there is a change of state. there is no further state to be changed colder than solid state, right? Therefore, Fg must be the room temperature. Okay, so that is all for the application of internal energy. We look at the heating curve and the cooling curve.